Okay. Hey class, how's it going? Hope you guys are doing well. This is my first little video and hopefully these go well for you. Sorry that the audio quality isn't amazing. I don't have a complete gamer streamer setup here at the school. So the mic's not going to be amazing, but I think you guys hear what's happening and you guys should be fine in understanding what's going on. I'm not going to tell you to write something down or don't write something down. If there's something that you think is valuable and you want to write down, please feel free. I might highlight what I think is important and you should note, but can't force you to do anything. We're going to be talking about Newton's laws. I wouldn't worry about this too much. I would worry about this. We've talked about Newton's first law, which is an object in motion will try to stay in motion unless acted on by another force. Object at rest will stay at rest unless acted on upon another force. And last time we learned about Newton's second law, which is that to calculate the force of an object, you do the mass times acceleration. And Newton's third law, you might have heard, is that every action has an equal and opposite reaction. You can see that in this little picture right here. The foot is pressing down on the earth. Meanwhile, while the earth is pressing down, while the foot's pressing down on the earth is pushing up on the foot. This is Newton's third law. For every action, there is an equal and opposite reaction. When objects interact, they exert forces on each other, and all forces arise from interactions. Forces always come in pairs. There's an action and a reaction, right? If no matter what, every force has a pairing with it. No, sorry, not whatever. Every applied force has a pairing with it, right? If you push or pull on anything, there's always some kind of other force that is included in the interaction. If you push on your table right now, your table pushes back on you. If you pull on a rope right now, there's a force of friction that pulls back on the rope. There's always some kind of push and pull when we have these forces, some kind of action and reaction. We call them action and reaction forces. So, like if we are pulling on this elephant right now, if I'm pulling 100 newtons on the elephant, what's happening is the elephant's also pulling 500 newtons on me. Same thing with the wall. If I'm pulling 500 newtons worth of force from the wall, it seems weird, but the wall is also pulling me for 500 newtons of force. It's the same type of force. This is the action, the elephant and the wall are the reaction in this case. It's a very common example and it's kind of weird to think about that the wall is pushing on you. Like it's not pushing on you the same way that like, you know, when you were in grade 3, you would push your friends around because you don't do that anymore. Yeah, it's pushing on you in the same way that there is a force that is literally pushing your hands. If there was no force that's pushing on your hands like push onto a wall, then your hand would go straight through the wall. So these are all really good examples of an action and reaction. When you hit a puck with a hockey stick, the puck actually hits the hockey stick back. When you're standing on a skateboard, the skateboard pushes up on you. When you fire a gun forward, the gun also goes backwards. When you throw a ball forward, you actually get pushed backwards. It might seem weird, but if I was like in midair and I threw a ball forward, me throwing that ball forward also causes me to go backwards. It's like recoil. And same thing with a car on the road. You're moving forward, but the tires on the road they have a force being pushed backwards. So think of this example. Imagine you're on a boat and you're trying to get into a dock. Think about what would happen if you jump off that boat. It's not just going to stay still. You push forward, you make your body move from here to here, but then the boat is going to move from here to here. That's the reaction of the boat. You move forward, the boat moves backwards. It's an unbalanced force on you, and then the boat moves backwards. There's an unbalanced force in the boat. Same thing with a skateboard. Right now, this is completely balanced, but the moment that you push backwards with your foot, there's an unbalanced force on the earth with your foot, right? You're pushing the earth, and in return, the earth pushes you or the board. So think of it in terms of a gun. If the force of the bullet is the same as the force experienced in the gun, why does the gun move very little but the bullet moves so fast? When you fire a gun, it's not just pew 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 like in the movies. There is always some kind of recoil from the gun, which always happens. It's kind of weird to think about though. How come the recoil doesn't go as fast as the bullet? And some of you might know the answer already, but if you think about it, this little tiny bullet goes really, really fast. How come the gun doesn't go as fast? Well, it might have something to do with the mass. Think of it this way. When you fire a bullet, there might not be that much force that's being applied right now. We have this formula, F equals ma, which we remember from before, where we know that the mass of an object and the acceleration of the object are related to each other. So let's try to calculate the acceleration of an object. If we do some rearranging, and if I have 100 newtons that's being used, if the bullet moving forward has a force of 100 newtons, then that means coming backwards, the gun's going to have 100 newtons worth of force as well. And we realize that since the gun is so heavy, it only shoots back at 111 meters per second squared. But since the bullet is so light, it shoots forward at 2,850 meters per second squared. This is acceleration, not speed, by the way. So even though this might seem fast, it is going really fast, but only for a short time. It doesn't actually move that much. Realistically, the gun only goes back like a couple inches or like an inch or two, but it's still the same amount of force that's being pushed backwards, which is crazy, right? Bullets are moving so fast to the point where they are killing things, and you have the same amount of force that's going killing things that's in your hands. Like if there's 100 newtons worth of force that's making the bullet go forward and killing things, that 100 newtons worth of force is falling backwards and hitting your hands. So I want you guys to try to think about how to use Newton's third law to explain the forces and result. The forces and result of a bird flying. When a bird is flying, how come that bird is like what are the forces that are being applied on that bird? When there's a head-on-head collision between two pool balls, what's actually happening to those two pool balls? I'm gonna go over this with everyone. That should conclude the video. If you guys have any questions, shoot me a message on Edsby. Have yourself a great day, you guys. Take it easy.